the second talk today, this afternoon, by Benedict Morrissey from the University of Chicago, and he's going to tell us about mirror symmetry for Hitchin fibrations associated to UNM.
Okay, so I'd like to start by thanking the organizers for the invitation. It's been a great conference so far, and in fact, there's one point in this talk where there's I can now even talk about some extra things learned this week. So the sort of this mainly going to be an example of, and it comes from a larger project that was done with Thomas Hameister and Jacquet in terms of thinking about there are certain branes on the Hitchin moduli space associated with spherical varieties. And the question is to understand the duality for these branes. I want to, so we've seen a bit of duality for branes in Thomas's talks, but I want to start by sort of talking about my view of the physics picture. So this really comes from sort of the Kapustin-Witten viewpoint on geometric Langlands. So the idea is you have two physical theories which n equals 4, d number of supercharges, if it matters, dimension of the space-time on which this is a theory, and there's also a gauge group. And the idea is that S-duality relates this to n equals 4, d equals 4 superdiagonals with the gauge group being the dual group. So these sort of physical theories are somehow far too hard for mathematicians to understand. And so we want to try and sort of get pieces of concrete geometric representation theoretic interest from these. And the first step, which is very common, is to do a holomorphic topological twist. And what this is really doing is there's some huge space of states. It's cutting down this space of states to some smaller space of states and operators, which will be more understandable. And there's actually here, there's a P1 of choice, well, there's a sphere of choices of this topological twist, which will ultimately turn out to correspond to the sphere of complex structures on the Hitchin moduli space. So in this case, which topological twist you do matters. And what you end up with is you end up with something which I actually won't describe. And then the next step is this is still a 4-dimensional field theory. We then consider this on a certain type of space-time, which is consider the theory on so the strip times a Riemann surface. And you probably want to scale things appropriately. And when this happens, essentially, so a field, we can usually think about some sort of G bundle and some sort of sections of associated bundles. If we think about it like this, and we think about X being really small, then if we fix a point here, we can say, well, at that point, we should have some G bundle on X with some fields. And this sort of changes the physical theory to what's called a sigma model, where you consider, and all this means is that the fields of the resultant theory correspond from maps from some space to another space. This being the space it's from, the space it maps to is the fields you can have on the Riemann surface. So you get a sigma model on, well, let's say the Hitchin moduli space. Where I'm not at the moment saying which complex structure we're getting, but certainly one way is that we will end up with an A model.
Great, CX. Yeah.
Right. I'm going to change this one to a C. They need to be the same. And a B model. Now, this is a slight simplification because if we really keep track of all the different possible twists, we get sort of a S2 family of different sigma models that sort of move around the different complex structures. And now that we're at this level, some of the categories might be easy enough to actually understand. So, or at least some of the objects, some of the categories. So on one side, we should have some sort of Mukai category. And on the other hand, some sort of derived category of coherent sheaves. And again, this is really still too hard to understand, as you know, and Mukai categories usually defined on nice manifolds. And in here, we have inside the objects, at least, we have the things that sort of are well behaved with respect to all the different holomorphic topological twists. And one sort of set of these well-behaved objects are BAA branes and BBB branes. So at this point, these are really concrete mathematical objects. So these will correspond to holomorphic Lagrangians. With a local system over them. And these will correspond to complex vector bundles with connection of type 1 with respect to each complex structure. So if you take one of the complex structures, you associated to that, you have a holomorphic structure on the complex vector bundle. And there's also a twister interpretation. And so these should be, on a hyperkähler submanifold. And well, these are geometrically interesting objects. So it's sort of natural to start trying to understand these objects. objects that sort of come naturally from the physical theory. And one way that this happens is in work of Otto Witter. And this is that boundary conditions of the 4D theory, probably with some conditions, should go down and give us boundary conditions of these theories, which correspond to these branes. And one sort of natural class of boundary conditions, we should probably, one class of boundary conditions that this should work for is boundary conditions associated to Hamiltonian G spaces. And so this is actually something where the sort of ideas have gone the other way. In the forthcoming work of Benedict, Jacquet Venkatesh, they sort of move from considering spherical varieties, which occurred sort of naturally in number theory, to starting to think about Hamiltonian spaces. Now, in our thing, we're actually going to try and get intuition going the other way by looking at special cases of these that have come up already in number theory.
Does it keep both BBB and BAA grays or just BAA?
So this is a good point. Given a Hamiltonian G space, we definitely know how to construct a BAA brane from it. I'll say that so. And conjecturally, there should be some sort of reasonable class of Hamiltonian spaces which have a dual and in which, in some way, one can construct a BBB brane from them. However, it is much less clear how to do that.
So you say they have a dual, but a dual group or a dual Hamiltonian G space?
Some class of Hamiltonian G spaces should have a dual Hamiltonian G check space. So inside here, we're going to look at, inside here are ones where the Hamiltonian G space, M, is equal to the cotangent bundle of a spherical variety. Now, inside those, there are the ones where the spherical variety is a symmetric space. And inside those, there's hopefully two examples we'll look at today. No, actually, inside those, there's one important example, which is the one associated with GLN cross GLN inside GL2N. And this is particularly good because of some conjectures of Nigel Hitchin on what the dual of this brane should be, more or less. And another important case is that, well, this is more that it's a case we considered and we made some progress with. So we here being Jacquet and I, which is I call it the Jacquet Rallis case. Here you consider GL n minus 1 and you embed it diagonally in GL n minus 1 cross GLN, where you do it as the upper sort of left corner. And right, and then you consider the quotient of this space by the GLN minus 1.
So that's a spherical writing of one symmetry space.
Yes. Okay. Okay, so and so somehow as mathematicians, we should be interested in ultimately trying to prove concrete geometric spaces that the dual properties that the dual should have. So Thomas talked a lot about graded dimensions of some Hom spaces between branes. Another important thing is that if we just consider what's happening in so this is the complex structure corresponding to Higgs bundles. Then the idea is that what can be seen in this structure should be Fourier Mukai dual. And essentially, what I'm hopefully going to talk about is how this works in 2 examples. Okay, so for the BAA brane from M a Hamiltonian G space, the idea is that the map from M a Hamilton G space with appropriate GM action. The idea is that the map of stacks from M mod G to the Lie algebra mod G, which is just the moment map, this Safronov shows is something called one-shifted Lagrangian.
It should be the G dual, right?
Yes, it's technically G dual, but I'm identifying G dual with G. And it's not really important what this means for this block, but when you consider maps from a curve to M mod J, and then post-compose with maps from a curve to G mod J, you get something that is derived Lagrangian in here. And in particular, this means that the image for G semi-simple, the image intersect the smooth locus is Lagrangian. And I also have to twist by some line bundle, and that's what the GM action takes care of. And of course, in more concrete cases, there's more concrete ways to see it. For instance, in the symmetric space case, you can often see these in fixed points from work of Oscar and Ragnar, right? Yes.
You said derived Lagrangian and said something about image. So
okay, so basically, derived Lagrangian, they usually drop the condition that it's an immersion. And in the example we'll see, we actually generally have a 2-to-1 map. Which is why the concrete statement is that the image of this intersects the smooth locus when G is semi-simple is Lagrangian.
In general, do you know something about the fibers of these maps in this?
Well, yes, Lagrangian, I mean, the Lagrangian condition tells you something. Basically, you shouldn't be able to have non-zero dimensional fibers for some appropriate notion of dimensional.
At the level of the course moduli space, how one sit inside the other?
So I'm, smooth locus. I mean, just go to the smooth locus, and that should mainly be the same on the course moduli space when G is semi-simple.
So it's a Lagrangian subvariety in any case.
The image will be, yes. Okay, so the first concrete example is I want to think about the Hitchin system for either the symmetric pair Gn cross Gn, Gn2n. This also is often called the Hitchin system associated to U and N. And as Thomas said, geometry of this was first analyzed by Shaposnik, and she described the fibers generically. So what this looks like is, this is the moduli space of tuples B1, B2, B1, B2. And the idea is that these are vector bundles on your curve C. And if you think about B1 plus B2, you have a map which corresponds to 0, B1, B2, 0, from B1 plus B2 to B1 plus B2, tensor with the canonical bundle or some other line bundle. And last time in Thomas's book, we saw that you can map this to invariance. One way to see this is just see this as a GL2n bundle, take all the invariance as a GL2n bundle, the characteristic polynomial, and you get a subspace of the usual Hitchin base corresponding to spectral curves, which are preserved by multiplying by -1 on the total space of KC. So let's do that. I'm just going to use U and N because it's shorter to write. So this has a map to the L2N Hitchin moduli space. This, you can take the usual map and go to A, and this is the space of spectral curves. And in this case, these are spectral curves where you have an involution corresponding to multiplied by -1 on fibers of the total space canonical bundle. Okay, so then we had that at least above a sufficiently nice point in here. Hypostonic. That fiber was equal to a disjoint union of part of x bar a. So we have that involution, so we can take the spectral curve xa and we can quotient by I. Then the disjoint union corresponds to subdivisors of xa intersect the zero section. And so this we could see from the sort of non-separated structures, when the spectral curve intersected the zero section corresponded to where the regular quotient was non-separated over the GIT quotient. And you had two choices each time as to which part of the regular quotient you went into. And so at each point in here, you have two choices corresponding, are you taking that element as part of the divisor or not? Now, so this geometric description we can recover for other symmetric pairs using the work of Thomas and I, and we hope that soon we'll be able to do it for spherical varieties. Somehow the trick is generically, you only intersect single hyperplanes. So you don't need to solve the full problem. You only need to understand what happens on hyperplanes. But what we can't do with the general theory that Jacquet did was that you can describe the map to the corresponding Hitchin fiber. And what this is, well, this is pic of xa bar. And the map is f of a point E is you pull back along the map from xa bar to xa bar mod I, and then you twist by the divisor. So how we should think about the fiber of this moduli space is, if the fibers of the Hitchin moduli space are roughly tori up to stacky structure and non-separated structure. And here you have many subtori living in that Hitchin fiber. Again, there's stacky structure and disconnected structure to think about. So if we want to consider the dual of pushing forward the structure sheaf here, which should be the BAA brane we're thinking about, then what we need to understand is, how do we do the Fourier Mukai duals of subtori, and secondly, of translation. Okay, so so here though is a point where I want to be more careful about what we mean by the Fourier Mukai duality. And so the way to do Fourier Mukai duality in a way that is fine, that you're not working with abelian varieties, but you have the stacky structure and you have this disconnected structure, is the theory of valence in one modes. And essentially, you should think about these as abelian varieties plus stacky structure plus disconnected structure. And and some conditions that I don't think I will say, but sort of the natural example is that if you have the stack Picard of a connected curve, then at every point, the automorphism's a curve that's just homs from the line bundle to its inverse, its sections of the trivial line bundle, which is just GM. So this maps to BGM. And in fact, we can break this up into two parts. I could say this is the Picard stack of degree 0, and then have the full Picard stack. And this has the fact that that if I consider this as a filtered object, here I have BGM, then I'm adding to it the Jacobian scheme. And then here I'm adding to it the integers. Oh, I've got them the wrong way around. Oh yeah. Well, the pieces are going to be the same, but let's make this correct. Okay. Yeah. Right. Okay. Thank you. Okay. So the sort of theory of Fourier Mukai duality for extending from abelian varieties to these was done by Lemon, Ranantoni, Rinken, and I think there's also some further results in Chin and Z. Okay, so the first result is how do we do translation and how does that affect Fourier Mukai duals? Okay, so translation is if I'm translating by a given object, that's equivalent to taking the convolution product with the skyscraper shape where I'm translating. And so here, the key result is that the Fourier Mukai product, Fourier Mukai transform swaps the convolution product and the tensor product. Okay, now there is something to be aware of. There's different normalizations for the Fourier Mukai transform, and I'm not going to get into that at all. Hopefully that will avoid there being more mistakes.
So this TI is defined from those stacks, or where does it?
So this translation is, the idea is for this stack, it would be I have a particular line bundle, and then that's this is a group object in stacks, the right notion of group object. And if I have a function on a normal abelian variety or a sheaf, I can translate it. Basically pulled back by the map, which is multiplication by A. And so I can do that on these as well. And so the idea is Fourier Mukai transform swaps convolution with tensor product. And so the idea here is that, let's actually write this down. So so this was proved by Mukai, and the proof extends to the balance in one motive case without any changes. That's perfect. Okay, and then the other thing that is happening, so this sort of deals with this translation partially, because twisting by D is translating by the line bundle associated to D. Then the next part is I have this map pulling back from the Picard here to the Picard here. And so this is actually dealt with in Hitchin's original paper on this conjecture. And the idea is that if A to B is a map of Balancing one motives or abelian varieties, then you have a dual map here. And if you want to take the Fourier Mukai transform of push forward of some shape, so this is the B Fourier Mukai transform, this is equal to this is equal to the pullback along F check of if you did the Fourier Mukai transform on A of the shape you started with. Okay, so at this point we can essentially do the transform and see what we get. We want I star of O of I, and I'm going to take the degree 0 part. I mean, somehow if I took all the parts, I'd get some huge object on the other side. We need to cut things down. And we're doing, should say O of MUNN, and we're going to take the part where the line bundle is, first line bundle is of degree 0. So then this is FM of a disjoint union over subdivisors of, again, intersecting the 0 section of say, well, an appropriate map of O of pick X bar mod I, and then we're convolving it with a skyscraper shape on B. Then this will be turn out to be the direct sum of the pieces coming from each of these. Okay, which are going to be well, this changes to tensoring with a particular line bundle. Fm of I and tensoring with Fm of O of D. And there may be a homological shift in our conventions. Okay, so this, we actually have a good description of what this changes into. The skyscraper sheet supported at a divisor, and that is so on pick over pick x bar cross x bar A, we have a universal object L. If we have a divisor here, we can restrict L to pick XA cross a given point, each point in the positive divisor, and then we can tensor them together. Now, if you're more familiar with Fourier Mukai for the Jacobian scheme, you know that usually you have to do some normalization factor to get it back to the right degree. And one of the great things about working with the valence in one motives is you don't need to do that. Somehow, when you started with D, that's of a particular degree. And on the other side, that turns into how GM acts on this object. And the GM action will be there's GM acts by power 1 to each element of D. So it precisely swaps the degree of the line bundle and the degree of the GM action. So tensor D and D L restricted to thick XA. Now, okay, and at this point we have something that is very close. After we put this together, we get something like in this case, when we're doing this with pick XA mod I, pick of XA, the dual sequence is the norm map, which has kernel the prim stack. And so if you start with something of degree 0, you end up with just the push forward of the sheet here. So something like sum over the divisors in XA intersect, Z, the tensor product of D and D of L, the universal bundle, restricted to XA from XA. Times D. And the idea is that this is very close to the direct Higgs bundle on the SP2N side. Basically, the difference is the direct Higgs bundle, which was developed by work of Hitchin and Levant, has here, you would have an extra tensor, you'd be tensoring by an extra term. And you also have that the SP2N Hitchin system isn't the prim, it's a translate of the prim. So the game is somehow, can we modify the other side so that we end up with precisely the Dirac-Higgs bundle, which is known to be hyperholomorphic. And so the answer is I'm pretty sure the answer is yes. The translation here will change to tensoring on the other side. So you just have some particular line bundle. And the tensoring in here, for each D, you have a fixed element that you're tensoring by. You can break it up into the different Ds. You can convolve on the other side, but what you're convolving by is constant on the fibers. Well, it's the dual of something convolving constant on the fibers, and it ends up just to be a constant sheaf supported at 0. So I don't actually want to write it out because certainly I will get a small error wrong, but the point is there should be some line bundle on the other side that gives you the actual Dirac-Higgs bundle. So modify mission side. Place.
That would be a global line bundle, right? On the UNN.
Yes, a global line bundle on the UNN. Right. So the other reason I don't want to write it up is I don't have this nice description of the line bundle. I just take the Fourier Mukai transforms of the things that you will have on this side and convolve them or tensor them in the correct way. And I mean, for instance, one prediction from mirror symmetry is that there should be a local system structure on this, but is there? I don't know. What I instead want to do for the rest of the time is talk about what changes when we start to think about other spaces associated to other spherical varieties. And essentially, Jilin and I developed a conjecture and about what representation replaces. Here we use the defining representation. Well, so I didn't say how the Dirac-Higgs bundle worked, but you have to feed it in a representation and you will get a Dirac-Higgs bundle. And somehow here, it was the defining representation of SP2N, and this had the property that the Dirac-Higgs bundle, this tensor, will always be over where the spectral curve intersects the 0 section. While on the other side, we saw that as coming from the non-separated structure of the symmetric pair moduli space. So what I think I want to say is what the conjecture is, and then that it holds in Jacquet Rallis for n equals 1, which Jilin calculated. So the conjecture is if we start with some, we start on one side with the BAA brane associated to T star X or G X. So the other key part of this was that the fiber was a union of abelian union of Benson-1 motives, or informally of abelian varieties. And that's going to be the case provided the regular centralizers are abelian. And in the symmetric pair case, this comes down to being quasi-split. And I do particularly want to mention now that, this is also one of the real motivations with my work with Thomas, is to get this geometry happening in the symmetric pairs case. And well, from the other day, we saw some of that geometry, and Thomas and I are planning on getting trying to get the other part working too. Okay, so in some cases, Sokoloridis, Venkatesh, Bemsve give a representation of GX check, the dual group for that spherical variety. And what we found worked in both cases was that if you had WX such a GX check representation such that T star of G check edge GX check WX was equal to G check wedge GX check BX, then it seemed that WX was the right thing to think about. So this works for this UNN example, and for GL2 cross GL1. Well, at least it gives you the right divisors. And so for something I learned at this conference, this is also the same representation that was coming up on Spencer's talk on endoscopy. And there's a few other tests that we were, well, there's at least one test that in the case where you don't have any non-separated structure, there the dual should just be a line bundle. And this, well, in the quasi-split cases, we think that this corresponds to where you don't have anything for WX and you just use the trivial representation. So this is one consistency check. And of course, there will, there'll be, the conjecture should be that there'll be some appropriate line bundle to add on this side, just as we had to change things around in the UNN case. I think I just want to give a few more examples of, a few more details on the Jacquet Rallis case.
So Benedict, one question. So you mentioned that for any Hamiltonian G space, you can get a BIA brane, but rather you just get the Lagrangian.
Yes, I
you don't get the local system, right?
Well, I mean, you can always just take, you can take the push forward of the trivial local system and get some perverse sheaf, certainly. Somehow, yeah, it's not clear. Okay, so the one more example with so GL1 into GL1 plus GL2. In this case, the sort of P star X mod G is equivalent to A, B, C, D quotient by And the GIT quotient becomes the invariant functions become A, D, and BC. And you again get this non-separated structure when BC is equal to 0, as you have two orbits, B equals 0 or C equals 0. Now, so that's the non-separated structure. On the other side, the representation is, so we had GL2 cross GL1. We take the representation V GL2, so the defining representation of GL2 times the defining representation of GL1. You then have that the space, well, this ABCD maps into minus A, ABCD in GL1 cross GL2. And then when you act with the Lie algebra on the tensor product, here you just get A minus A. So the action is by this then maps to BC D minus A. And here, this will intersect the 0 section when one of the eigenvalues is 0. So when the determinant is 0. Which is precisely when BC equals 0. So here we see the intersection with the 0 section again matching the non-separated locus. And this is sort of what made the machine work in the UNN case. However, this time the details of the calculation are even more complicated. So we're not totally sure that we can move line bundles back and forth on either side to get precisely a duality. Okay, that's all I wanted to say today.
Yes. On board 12.
Yep.
Can you explain how to see the symplectic root? Is it in the support being on the image?
Right. So it's that the find another board. So actually, at this point, I'm able to refer back to the paper that started it all with stable bundles and integrable systems. Showed, should mention it at least once this conference, showed that if you think about the SP2N moduli space inside the GL2N Hitchin moduli space, then on fibers, well, so then above. So again, we have that the SP2N Hitchin moduli space, this corresponds to the spectral covers fixed by the involution multiplying by -1 on the fibers. Now, in this, then you can ask, okay, we have a point here, and we consider the same point here, and here we have a fiber looking like pic of X bar. Then if we have R as the ramification divisor for XA mapping to X, the fiber here, so inside here we have the prim variety. And if I have a line bundle here, L line bundle corresponding to the point here by the spectral construction, then we have L tensor with, I want O of R, and I want plus or minus 1/2. This is actually going to be in the prim, assuming I've got the precise factor to translate by right. And so what we have is so the fact that we get the prim is about the fact that we have something to do with sp2n. We don't get, as Thomas noted for the UN+1 case, we don't get, for these normalizations, we don't get the sp2n Hitchin moduli space directly. We get a translate of it. And then, as I said, one way you can then phrase this is that if you tensor by the right thing on the other side, you'll actually get the sp2n Hitchin moduli space.
So, sorry, I'm listening. What's a tempered spherical G mod H? What does it mean, tempered?
So tempered means abelian regular centralizers. I should warn you that you were talking to Spencer the other day, and Spencer was using a slightly different definition of tempered.
And then this one is tempered, I presume, this Jacquet, yeah.
Yes.
And do you understand what kind of Higgs bundles this will be?
Jacquet Rallis understands the Hitchin fibers for this case in his paper on the Jacquet Rallis fundamental lemma. So in this case, the automorphism group is trivial. So the regular centralizers are trivial, which means the fiber is a set of points. And Jacquet Rallis actually tells, well, Jacquet Rallis actually says precisely what the points are. One way that it can be seen is that basically take the regular quotient. Now, because J is trivial, the regular quotient is actually the set of regular elements. And, well, it's the same. Essentially, the maps to the regular quotient turn out to be the same. So as long as you're sufficiently as long as you don't go into the hyperplanes for too long, it ends up just looking at how many times do you sort of cross this type of divisor, and you'll have a number of choices each time. But yeah, it's a discrete set that can be described very explicitly.
At the beginning, you said there was some class of maybe spherical varieties or Hamiltonian spaces where you could get in the other side also. I mean, there is a dual group attached to it, but you said you can actually get a spherical variety.
No, I said a representation.
Oh, that's the thing that you were.
I said two things. One was that I said that there's expected to be a set of Hamiltonian spaces, such that on the other side you have a dual Hamiltonian space.
I was referring to that. Yes.
Okay.
So there is a dual group, right?
Mm-hmm.
But you will have a space there. What is the space? I mean, this Hamiltonian space.
So all I will say is that in some cases, so firstly, on the website of Jonathan Lang, there's a list of examples. And if it appears on the table, it's an example. Then the other one is that I think in the cases where there is a Vx, it ends up being G check, wedge, Gx check.
So this Vx, this representation, the tempered condition is important or not?
So for me, I'm introducing the tempered condition because otherwise you will be in the singular locus of the Hitchin fibration, and your fibers won't look like Fourier. And who knows what the analog of the Fourier Mukai condition is here. In fact, both of these examples are very carefully chosen. I mean, one thing is, even if you go to UN+1, you don't end up in the very singular locus, but you still have a singular spectral curve because you have the zero eigenvalue intersecting. So there you can, I mean, there Rinken has sort of developed a Fourier Mukai track. Well, no, sorry. Here the singularities are mild. It's classical that there are versions of the Fourier Mukai transform, but you have to change. You have to do one of those. And Rinken has shown in a much higher generality that you can deal with singular curves for GLN. And then there's some promising work, very promising work by Mao Li and also Rinken Fedosov on sort of what does the Fourier Mukai transform look like at singular fibers. The curve still has to be, the Cameron curve or the spectral curve still has to be reduced. But the issue, right, so I'm doing tempered, and also choosing examples where you actually land in the locus where things are non-singular for the ambient group. There's lots of other meanings of tempered, other equivalent conditions. There's a series of papers by Benoit and Kobayashi, which gives several different conditions, but I'm not aware of what they mean.
So in this case, you are relating branes defined by the symmetric pair to branes corresponding to the Nadler group. So the conjecture for Hamiltonian G spaces would be that these branes corresponding to Hamiltonian G spaces are dual to branes corresponding to this dual group, right? Or...
Yes. So in this Jacquet Rallis case, the dual group is the group you start with, and that's because the base is the entire thing. But yes, one should expect. The expectation is that up to some sort of translating and convolution, you should get a direct Higgs bundle for this Wx when it exists on the Gx check Higgs bundles.
So what role should play the dual Hamiltonian G space, if any?
Right. So the answer is, of course, that there should be some way of getting the BBB branes from the dual Hamiltonian G space. But somehow, I mean, even in existing literature, you know, in these cases where we have a representation, somehow people have been studying things from the representation, and hopefully eventually you'll be able to see things from whatever the dual Hamiltonian G space is, but I don't have any insights here. Even my understanding of Wx is looking at tables.
Any further questions? All right, well, thank you very much again.